Section 6, we're going to work on solving exponential and logarithmic equations. And we've already talked about what these look like. An exponential equation obviously has your variable as an exponent. They can take many different forms, but that's the key element. If we add something like this, y is equal to a times b to the x power, this is what makes it an exponential equation. The variable that I'm solving for, x, is an exponent. Equally, if I had y is equal to a times logarithm base b of x, this is a logarithmic equation. I've got a logarithm and my variable is in the logarithm. And as you've already learned, extraneous solutions are solutions we solve for with proper algebraic work and yet aren't actually solutions because when plugged back into the original equation, they don't work. So because there are domain restrictions, particularly in logarithms, and we're working with exponentiating and taking logarithms of either side of equations, there is the potential that we will have extraneous solutions, much in the same way as we were squaring and square rooting problems. It created the potential for an extraneous solution, so it's something to stay aware of and something you'd want to check for at the end of the problem. So an example of a logarithmic equation that we might use for some sort of real-world application, we're talking about apparent magnitude of a star can be measured with this equation, and in this case, when they supply me the magnitude of the star, then I can say the diameter of the telescope that was necessary in order to create that magnitude. So we'll work on that in a little bit, but let's go through how we solve logarithmic and exponential functions. So we're basically going to go through two different methods for each exponential and logarithmic equations. And we're going to talk about a couple of rules that really kind of make sense, that if I have two items with the same base that are equal, two x powers with the same base that are equal, then it stands to reason that the exponents must be equal. The key element in this is that the bases have to be the same. Okay, so if I can create a situation where I've got the same base, essentially what that means is I can take the base back out of the problem. Okay, so in this case, I don't have the same bases, but you could see that 25 is a power of 5. So with a little bit of work, I can make these have the same base. 25 is 5 squared. When I take a power to a power, I multiply the exponents. So this will be 5 to the 2x minus 12 power. And now I can just take these bases and get rid of them. So I know that x minus 4 must be equal to 2x minus 12. If I subtract x and add 12, I'll get x is equal to 8. Now I'd plug that back up into my original equation. This would be 5 to the 4th power. 8 minus 4, 5 to the 4th power is equal to 25 to the 2nd power. And again, if we think about 5 to the 4th is equal to 5 squared to the 2nd power, when I multiply these exponents, I'll get 5 fourths is equal to 5 fourths. So that checks out. Okay, in this particular problem, I can do the same sort of thing. Here I had to rewrite one of the bases, but over here I'm going to have to really rewrite them both. But you can see that 8 and 32 are both powers of 2. So 2 to the 3rd power to the x minus 1 power would be equal to 2 to the 5th power. To the 3x minus 2. Okay, and when I take a power to a power, I multiply the exponents. So this is 2 to the 3x minus 3. Is equal to 2 to the 15x minus 10. And now I can get rid of the bases. 3x minus 3 is equal to 15x minus 10. If I subtract 3x, I'll get 12x here, and I add 10 is equal to 7. So x would be equal to 7/12. Okay? So the key for you is that when you have equations that have exponents as the variable in an exponent on both sides of an equation, what you're going to have to do is rewrite the bases to be powers of the same number Once the bases are the same, then you can get rid of them, which is what we did in this step on each case. And then we can move on and we can solve for our variable. So practice that. Go ahead and do problems 7 through 9, and then come back and we'll work on another method. So in this type of a problem, I have my exponent is a variable, but only on one side of each equation. So in this case, I want to take a logarithm of each side. And if you remember in an earlier section, we talked about the idea that log base b of x is equal to x. So logarithms cancel out the base of a power. What I need to do in this case is I want to take a logarithm of each side, but the key to this is knowing what logarithm do I want to take. And I want to match the logarithm to the base of the power. So in this problem, I'm going to take a logarithm base e, that's a natural logarithm. And because I do that on the left side of the equation, I'm also going to do it on the right side of the equation. I do that because the logarithm cancels the base of the power and I just get negative x is equal to the natural log of 5. So x would be equal to the opposite of the natural log of 5. So if I went ahead and took the natural log of 5, multiplied it times negative 1, I'll get the solution. I'm not going to do that. That's something you do with a calculator pretty simply, and you guys can do that on your own. Up here I'm going to do a logarithm base 8 of 8 to the x power, and therefore I'll do the same over here, 8 of 20. X will be equal to log base 8 of 20. And I've already learned the change of base formula, so I can also do this in my calculator, log of 20 over log of 8. Also, this remains to be done in the calculator. I'm not going to go ahead and do that, but that's something you can do as you practice. So go ahead and do problems 15 through 17, and then come on back and we'll solve a word problem using exponential functions. So in this case, we're going to use Newton's law of cooling, where we've got that our target temperature would be equal to our starting temperature. So let's just make sure we understand what everything is. T sub 0 is the starting temp, the temp at time 0, right? That's why it's a 0. And then T sub R is the current temperature, ambient temperature. Okay. And then we have R, which is a rate. Okay. So when we have the situation, we were driving on a hot day and our car overheated. It overheated at 280 degrees Fahrenheit. That is then my starting situation, 280 degrees. It can be driven again at 230 degrees. That was my target temperature. If R is equal to 0.0048 and it's 80 degrees outside, that means T sub R is equal to 80 degrees. How long in minutes do I have to wait until I can continue driving? So I know that 230 is equal to 280 minus 80, times e to the negative 0.0048 t power plus T sub R, which would be 80 degrees. Right, so if I subtract 80 from either side, right, that would be 150 is equal to 280 minus 80 is 200 times e to the negative 0.0048 t power. And the way I'm going to solve this is to take a natural logarithm of either side. Oh, I'm sorry. Before I do that, I'm going to divide by 200. So for me to solve this, I'm going to go ahead and divide by 200. So 150 divided by 200 will be equal to e to the negative 0.0048 t power. Now this is 0.75, or we could say it's 3/4, either way you want to look at it. 3/4. And I'm going to take a natural log of either side of this equation. I did that because the base of my power is e. This is going to cancel with that, and it'll be equal to negative 0.0048 t. And over here I'll have the natural log of 0.75. Okay, if I go ahead and solve this, I'm going to have the natural log of 0.75 divided by negative 0.0048, and that will be equal to t. So if I go ahead and pull up a calculator, so I'm going to take the natural log of 0.75, and then I'm going to divide it by the opposite of 0.0048, and I end up basically with getting 60. Okay, so it looks like in time I'm going to have to wait about an hour. Okay? So moving on to our logarithmic functions. If we want to go ahead and solve the logarithmic functions, again, we've got this rule here that says that when I have logarithms of the same base on either side, you can see then that if the log base b of x is equal to log base b of y, then x must equal y. Okay, so it's the same sort of idea that we had with the exponential functions, and if you really want to think of this in a more simplistic way, I'm allowed to introduce a logarithm to either side of an equation, and if I can put it into either side of an equation, I can take it out of either side of the equation as long as they're the same base. So in this case, you just take log of 5 off either side of the equation. I'll get 5x plus 9 is equal to 6x, so x would be equal to 9. In this case, I would get 4x minus 7 is equal to x plus 11 by removing the natural log from either side. If I subtract x, I'll get 3x is equal to 18. So then x must be equal to 6. Now again, we have this problem of extraneous solutions. So I might want to plug these back in. So I'd get natural log of 24 minus 7 and the natural log of 6 plus 11. Well, 24 minus 7 is 17. 6 plus 11 is 17. That checks out. So this is a good solution. If I plug the 9 in here, 5 times 9 is 45, plus 9, and 6 times 9 is 54. 45 plus 9 is 54. That checks out. That's a good solution. But as we look at this one, I have 2x minus 7 is equal to 3x minus 9. And if we subtract 2x, I'll get x. And if I add 9 to either side, x is equal to 2. And if I plug this back in, I'll get 4 minus 7. And over here, I'll get 6 minus 9. And you might think, well, negative 3 is equal to negative 3. That's fine. But the problem with it is I can't take a logarithm base 5 of a negative number. There is no power that I can take 5 to that would equal negative 3. It's not possible. Okay, so when you have domain restrictions on these items, like you have domain restrictions in even roots, you can't, if you end up with a value when you plug it in here, can't be done, that's an extraneous solution. Okay, so you want to be checking your solutions to see if they're extraneous. Go ahead and do some practice. Do problems 27 and 28. Make sure that you check for extraneous solutions. So the last method that we have for working on these is exponentiating either side of an equation. And the idea there, again, is that if I have b to the log base b of x power, that will equal x. So if I have a logarithm with a base b, then I can take and exponentiate either side by taking that logarithm and making it the exponent on a power with the base of b, and these will simplify. Okay, so this is the rule I'm going to be using in this part. So I have a log base 4. I'm going to take either side of the equation and make it an exponent on a base of 4. Okay, again, how did I know what base I wanted for my power? It's the same as the base of the logarithm. So when the bases match, these cancel each other out. So here I'll just get x is equal to 4 to the negative 1 power, which is 1/4. So when you look at this particular problem, I can't really go right to this step without somehow combining these guys, but happily I do know that if I have logarithms that are being added together, I could condense this and make them a single logarithm where my items are being multiplied, negative x times x plus 10. Right? And if I now exponentiate either side, so I'll have 4 to the log base 4 of, this might as well be negative x squared minus 10x. That's sort of where we're headed here. That'll be 4 squared. Okay, and this cancels out that, so I'll get the opposite of x squared minus 10x is equal to 16. Quadratic function, so I'm going to put it all on one side, make it equal 0. I add x squared and I add 10x, and now I want to factor this. So I want factors of 16 that add up to be 10. That would be 2 and 8. And then x will be equal to negative 8 and negative 2. Okay, so we're combining a couple skills in here. The key is, right, I don't want multiple logarithms, so I can use the condensing properties that I learned earlier to combine these all into a single logarithm. Once I've done that, I can exponentiate either side. Okay, so you do want to call on the other skills you've learned when you're working on these problems. Go ahead and get a little practice. Do 36, 37, 40, and 41. Come on back and we'll wrap up the lecture. So back to my astronomy problem. I'm going to be working with this function here. The magnitude m of the dimmest star that can be seen by my telescopes is, so the magnitude would be 5 times log of the diameter of my telescope's objective lens plus 2. So if my telescope can reveal stars with a magnitude of 12, so 12 goes in for the magnitude, 5 log d plus 2. So I'm going to subtract 2, and I'm also going to divide by 5, log d. 10 divided by 5 is 2, is equal to log of d. So in this case, I'm going to exponentiate either side, right? So this is a log base 10. It's a common logarithm. So 10 squared is equal to 10 to the log base 10 of d. 10 squared is 100, is equal to d in millimeters. So this is 100 millimeters. Okay, so again, isolate the logarithm, exponentiate either side of the function, and you can solve a logarithmic equation.